Now next, let us discuss the laws of reflection. I have drawn a red parallelogram. This defines the plane upon which reflection is taking place. Okay. So let this be plane M1, M2, M3, and M4. Light from point A is falling upon this plane and gets reflected to a point B. Okay. I'm going to draw normals from A and B towards this plane. Let this normal meet here. Let this normal meet here. Let this point be C. Let this point be D. And let light be reflected upon the point O. If I draw a normal at point O, I'm going to call it N. Okay. Now I'm going to assign values for these points. Okay. In order to assign values, first I need to set this in a Cartesian coordinate system, and this is defined here. Let this be the x-axis, this be the y-axis, and this be the z-axis. And D is set as the origin of the system. So I'm going to set D as the origin of the system. Now, the distance from D to C, let it be small d. The distance from D to A, let it be small a. And the distance from C to B, let it be small b. Okay. Now, I said that light is reflecting upon this surface M1, M2, M3, and M4. So this point can be arbitrary, can be anywhere upon this plane. Okay. And this plane is actually the XZ plane. Okay. So light can reflect upon any point upon this XZ plane. So O is a variable actually. The point O can vary along this line. Okay. So I'm also defining another point. Let this point be P. Light need not reflect upon this path AOB. It can also reflect upon APB, right? So it can choose any path. For generalization, let us select the path APB. This will be your angle of incidence I, and this will be your angle of reflection R. Okay. Now, since I have stated the positions, let us find the coordinates of these points mentioned here, A, B, C, D, O, and P. Okay. So the coordinates of A can be written as A in x-axis is 0, in y-axis is A, and in z-axis is 0. B can be written as in x-axis it is D, y-axis it is B, z-axis it is 0. C can be written as x-axis it is D, y-axis it is 0, z-axis it is 0. D is the origin. O is a variable. Okay, so it can move along the line, right? So I can define it as x, comma, it won't vary along the y-axis, so 0, comma, and it is restricted into the line. Okay, so here z will be 0. Now P can vary along any point on the plane, so that becomes x, comma, 0, comma, z. Okay, we have defined the coordinates of these points. In order to use Fermat's principle to derive laws of reflection, Fermat's principle uses this variable called d delta by ds is equal to 0, right? So we need to find out what is the optical path length, delta. The optical path length delta it is written as the product of refractive index and the geometrical path length. So here I can write mu into, what is the optical path length? Mu into, so we have assumed that light takes a general path APB. I'm going to write mu into AP plus mu into PB. Okay. So I write mu into AP plus PB. Now, here, since mu is a constant, it won't vary in this principle, right? The derivative, mu being a constant, it doesn't affect this variable. Hence, I'm just going to calculate what is the path length AP plus PB. So the path length L is given as AP plus PB. It can be written as, if you have 2 points with coordinates A with coordinates x1, y1, z1 and P with coordinates x2, y2 and z2. The length between these 2 points can be written as square root of x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. So using that, I'm going to write AP is equal to x minus 0 the whole square plus 0 minus a the whole square plus z minus 0 the whole square raised to 1 by 2 plus PB. I can write d minus x the whole square plus b minus 0 the whole square plus 0 minus z the whole square whole raised to 1 by 2. Okay. Simplifying it, I can write L is equal to x square plus a square plus z square whole raised to 1 by 2 plus d minus x square plus b square plus z square whole raised to 1 by 2. Okay. Now, understand that the path length L can vary along any point on the plane M1, M2, M3, M4. Hence, L can vary along x-axis and z-axis. So, Fermat's principle takes partial derivative. We need to vary it along both x and z. So, first let us vary it upon x. Initially, first let us vary it upon z. Partial derivative dou L by dou z at constant x can be written as, partial derivative can be written as 1 by 2 into 1 divided by x square plus a square plus z square raised to 1 by 2, again into z needs to be again partially derived to z. That was the first term plus next term again 1 by 2 into 1 divided by d minus x the whole square plus b square plus z square whole raised to 1 by 2. Okay, fine. Here 2 cancels out. Oh no, here I haven't written the next term into 2z. and z is a common term, can be taken outside, you get z into 1 divided by x square plus a square plus z square whole raised to 1 by 2 plus 1 divided by d minus x the whole square plus b square plus z square whole raised to 1 by 2, right? Now, from this product term, I have mentioned that according to Fermat's principle, this term is equal to 0, right? This term is equal to 0. Now, if we use, let us see the term in the braces, okay? Here, A is a point, it's the distance of point A from the origin. Okay, this is a positive term. So this term will be again positive, and this 1 by term will remain positive. Here in this term, B is the distance from point C to point B, that is positive. Hence, this sum point term will be positive, and this 1 over the positive term remains positive. Okay. Hence, the term in bracket can never be 0. This implies that z must be equal to 0. Z must be equal to 0 implies that light ray can reflect only upon this line, right? Light cannot move through the z-axis either in the positive direction or in the negative direction. It cannot move in the z-axis. Hence, it can vary only in the x-axis. That means it can move only along this line. So, light can be reflected upon any point on this line. Okay, upon any point on this line. This means that the reflected ray, this means that the incident ray, the reflected ray, and the normal to the point of reflection will all lie on the same plane. Will all lie on the same plane, the plane that is perpendicular to M1, M2, M3, and M4. And this is the first law in reflection. The first law of reflection states that the incident ray, reflected ray, and normal to the boundary of incidence and reflection all lie in the same plane. Now let us move to the second law of reflection. We are going to derivate L with respect to x. So, dou L by dou x at constant z equal to 0. I can write the value of z, right? So I get it as 1 by 2 into 1 divided by x square plus a square. The next term has become 0 to 1 by 2 to 2x, right? Plus 1 by 2 into 1 divided by d minus x the whole square plus b square plus, x term is 0 raised to 1 by 2 into 2 times d minus x into minus 1 of this minus x, okay, is equal to 0. Okay, 2 can be cancelled out, which means that x divided by x square plus a square raised to 1 by 2 is equal to x minus d, no, is equal to, taking negative sign, I'll get d minus x divided by d minus x the whole square plus b square raised to 1 by 2. In this figure, using Pythagoras theorem, I can calculate what is sine I and sine R. So sine I can be written as here sine I, right? It can be written as opposite side by hypotenuse. Opposite side is like similar to DO divided by hypotenuse. Okay, DO is given as x divided by hypotenuse square root of x square plus a square, right? Okay, similarly, sine R can be written as d minus x root of d minus x divided by square root of d minus x square plus b square. Hence, in the derivation of second law, I can substitute this as sine I is equal to sine R. Taking sine inverse on both sides, I get I equals R. And this is the second law of reflection. That is, the angle of incidence is equal to angle of the reflection. We have thus derived the two laws of reflection. With that, we come to the end of today's class. Thank you.